Okay, fine. So this is our first lecture on Paper-3 of Energy Auditor and Energy Manager Examination, which is conducted by Bureau of Energy Efficiency, Government of India. This is a national certification examination for energy auditors and energy managers conducted every year. Right. So let us begin with our discussion. So the third paper is energy efficiency in electrical utilities, and we are going to discuss the chapter number 1. The chapter 1 is regarding electrical systems, in which we are going to discuss regarding the topic which is introduction to electric power supply system. So what is we are going to discuss here is the introduction to electric power supply systems. Then we are going to discuss the power generation plant, then the transmission and distribution lines and cascade efficiency, also industrial end users. So let us begin with the introduction to our electric power supply system. What is electric power supply system? It is the system through which the power is generated at one place and consumed at some other place. It comprises of generating station, transmission lines or network, distribution lines or network, energy control centers, load or consumers. Okay, so electric power system is nothing but it is a system which simply it is a simple system which is basically helping to generate the power, to transmit the power, to distribute the power, and to consume the power, right? So it has several components of starting from the generating station to the transmission system to the distribution system to the control system and to the consumer or the load centers. Okay, fine. So there is generation of power, there is transmission of power, there is distribution of power, there is consumption of power, and of course at several stages in between there is control of power. Now let us discuss regarding the generation of power. The power plants are used to generate the electric power. Now there are several types of power plants popular, and this is so let us talk about classification of power plants on the basis of fuel that they are using. So we have the classification of power plants on the basis of fuel that they are using to generate the electric power as thermal power plant, nuclear, solar, hydel, geothermal, wind, and some other also. So we have coal-based power plants, we have gas-based power plants, we have oil-based power plants, water-based power plants, nuclear-based power plants, solar, there are several others like wind also. So water based is our hydel power plant. Nuclear based power plants are those which are using radioactive substances as the fuel. This coal, gas and oil falls in the category of thermal power plants. Solar is a power plant which is now getting very popular, which is actually a renewable source of power. Wind is also a renewable source of power. Now we have some conventional generation of power which is actually using fossil fuels like coal, oil, gas, etc. So and we have some unconventional generation of power which is actually using renewable sources for generation of power like water, geothermal, hydel, solar, etc. Now the 70% of power in India is thermal power which uses coal. 70% of the power in India is thermal power which uses coal. Thermal power plants has overall efficiency of only around 28 to 35%. Okay, so they are not that efficient power plants, thermal power plants. Okay, so let us talk about this coal-based thermal power plant, which is a very popular power plant in India, which is using the coal as the main fuel. The coal is pulverized or crushed to the consistency of talcum powder. It is crushed fine, and the powdered coal made in the form of powder, and the powdered coal is blown into water-walled boiler, where the powdered coal is heated up to temperatures above 1300 degrees C. This in turn will convert that water into high pressure steam. That high pressure steam will be used to rotate the turbine, which is connected to a generator which ultimately generates the electric power. This is a very basic schematic of a coal based power plant, where we can see that the coal is first pulverized to the consistency of talcum powder, and then it is blown into a chamber, into a boiler, where it is burnt above temperature 1300 degrees C, which in turn raises the temperature of the water, which converts the water into high pressure steam, and that high pressure steam is used to rotate the turbine, which ultimately is connected to a generator, which ultimately generates the electric power. So this is a basic schematic of a coal-based power plant. Now let us discuss a very important and concept that is called heat rate. This is an important question which is asked in your examination. Heat rate. What is heat rate? It reflects efficiency of the generation. It is the amount of heat input in kilocalorie or kilojoule for generating 1 kilowatt hour, that is 1 unit of electrical power. So how much amount of heat energy is actually you are using to generate 1 unit of electricity? That is the heat rate. How much amount of heat you are using to generate 1 unit of electricity, that is the heat rate. So let's suppose there is a power plant A and there is a power plant B. If the A power plant is generating 1 unit of electricity by consuming more heat, and B power plant is generating the 1 unit of electricity by consuming less heat, so definitely the efficiency of power plant B is good, because the heat rate is low. So heat rate is inversely proportional to the efficiency of the power plant. Now let us understand some very basic thing, that as we know that 1 kilowatt hour, this kilowatt is nothing but it is 1000 watt hour, as we can replace this kilo by 1000. Now this watt hour, the hour is replaced here by 60 into 60 seconds, 60 minutes into 60 seconds. Hour is converted to seconds, so this will be 3600 kilowatt second. This is 3600 kilowatt second. This kilowatt second, this watt second has a special name which is joule. So this is 3600 kilojoule. So 1 kilowatt hour is equal to 3600 kilojoule, 3600 kilojoule. So this 1 kilowatt hour is 3600 kilojoule, and it is also 860 kilocalorie. As we know that power is equal to work done by time, and as we know that power is watt, this work is joule, this time is second, so simply we could get that joule is equal to watt into second. So this watt second is replaced by joule. So 1 unit of electricity, that is 1 kilowatt hour, is equal to 3600 kilojoule, is equal to 860 kilocalorie. So heat rate is inversely proportional to the efficiency of power generation. Now moving to the next stage, that is transmission and distribution of power. At the power generating station, the voltage of the produced power is in the range of 11 kV to 33 kV at a frequency of 50 Hz. This generated voltage is stepped up to higher voltage level for transmission on cables, stepped up to say 220 kilovolt, 400 kilovolts, and so on. So there are transmission lines which are high voltage transmission lines, extra high voltage transmission lines, and high voltage DC, which is HVDC transmission lines. There are also few other transmission lines which are sub transmission voltage levels, or sub transmission lines which are carrying the voltage at a level of 132 kilovolt, 110 kilovolt, 66 kilovolt, or 33 kilovolt, and so. The distribution transmission lines or the distribution voltage levels are usually around 11 kilovolt, 6.6 kilovolt, 3.3 kilovolts, and so on. So at the distribution, the step down transformers are used at the distribution substation simply to reduce or to step down the voltage. Okay. So this is a basic schematic of transmission and distribution network. So as we can see that the generator is generating at say 10 kilovolt level the power, and then there is a use of a step up transformer which is actually stepping up, increasing the voltage level to say 400 kilovolt, and now there is a use of a step down transformer, step down, step down, step down, and ultimately it is getting distributed to several industrial loads like big industries, medium, small, and the domestic consumers. Okay, so this is a basic schematic just for your understanding. Now the important concept here to learn or understand is this, that why high voltage transmission is preferred. Again, this topic is important for your examination, that why high voltage transmission is preferred, or the customers are only requiring either 230 volts, or they require just 415 volts, say. So why this extra high voltage transmission is actually needed if the consumer is not in a need of those high voltages? It is only asking for 230 volt or 415 volt, that's it. So why this high voltage transmission is done? Well, there are some benefit, definitely. So as we know, see, after the generation, the power is generated by the generator at a certain voltage level, and then it is immediately stepped up. Immediately the voltage level is increased by using a step up transformer. So as we know from our basic knowledge of electrical engineering, that the step of transformer, let's suppose this is a transformer, this is our step of transformer. So as we know, let the voltage level here is V1, let the current here is I1. As we know that the transformer is a very highly efficient device which is not having any moving mechanical part, and it has a efficiency of almost 99.999% or 99.5% or 100%. So whatever power is delivered at the primary side, that is V1 into I1, is simply equal to the power at the secondary side, that is V2 into I2. So see, it is basically simply, so it is a step of transformer where it is raising the voltage level from V1 to V2. It is raising the voltage level from V1 to V2. So whatever power is, it is having a efficiency of almost 100%. So assuming that whatever power is fed at the primary side is getting delivered at the secondary side. So definitely V1 I1 is equal to V2 I2. So this relation must hold. This relation must hold for a step up transformer, that V1 I1 is equal to V2 I2. Okay. Now what if, so if the V2 is increased, the voltage level, it is a step up transformer, it has increased the voltage level, the V2 is high compared to V1, the V2 is increased, so definitely I2 has reduced. So definitely I2 has reduced, because the multiplication, because it is not the product V2 I2 is not going to change, it remains constant, it remains same. So if the V2 has increased by using this step up transformer, so definitely this I2 has decreased at the secondary side of the transformer. Exactly. So what is the benefit of reducing this current drawn? What is the benefit of reducing this current drawn? Well, when the current drawn is reduced, then definitely the size of the cable, the rating of the cable is going to reduce. We will be using a lower cross section area cable 1. And the most important thing, the line losses, the I2R losses, the power loss, the I2R losses will be reduced because the current has reduced. So there are two benefits. The size of the cable has reduced, the rating of the cable has reduced, as well as the I2R losses has reduced. So this is the advantage. So that is why we are transmitting the power at higher voltage levels. Okay. So we have already seen in the previous schematic. There are different voltages levels. Okay, voltage drop in a line depends upon what factors? What factors the voltage drop in a line is going to depend? Well, from the common sense, you can easily see that it is going to depend on the the length of the line. The voltage drop will depend on the length of the line, the resistance of the line, the reactance of the line, the current drawn or the current flowing from the line. The reactance of the line means the inductance of the line or the capacitance of the line. Okay. Now power loss in a transmission line, the power loss in a transmission line is given by I2R. Now here, very important to note that do not use Ohm's law, I is equal to V by R, to know or to interpret this power loss in a transmission line. please note that power loss in a transmission line is only and only I square R. You should not replace this I or this R by using the Ohm's law. Somebody will do what? He or she will simply apply the Ohm's law. I is equal to V by R. So they will replace this I by V by R. So they will get power loss is equal to V square by R. So that would be a wrong. So then you will end up in a wrong interpretation. Again, do not use that. Do not replace this I. Do not replace this R. The power loss in a transmission or distribution line is only I square R. Okay. It is not V square by R. It is not V into I. Simply. So why so? Because see, when we are talking about the power loss in a transmission line, so it is definitely going to depend on the physical properties of the transmission line which is offering the resistance. Point number one. Second, whatever the voltage may be, if the circuit is not closed and if there is no current flowing from the transmission line, there is no meaning of any voltage drop. So it is the current flowing from the transmission line and the physical properties which is offering the resistance in the transmission line are the two factors which are critical and which will decide the power loss in the transmission line. So we are going to take this I square R as the power loss in the transmission or distribution line only. Okay, fine. So now let us understand a beautiful concept and let us see the magic that what if the voltage level is increased from 11 kV to 33 kV. What if I claim that the voltage drop in the line will be reduced by a factor of 1 by 3. We will see how. I also claim that the line losses will be reduced by a factor of 1 by 9. Let us see how. Okay, so as we know that power loss is equal to I square R. Okay, and we also know from our previous discussion that I1 V1 is equal to I2 V2. Okay, holds for a step up transformer or any transformer. It is this relation holds. I1 V1 is equal to I2 V2. So let so as we are talking that the voltage is increased from 11 kV to 33 kV. So V1 is 11 kV, V1 is 11 and V2 is what? 33. So let us use this V1 11 and V2 33. If we replace V1 by 11 and V2 by 33, we will end up with a beautiful relationship between I1 and I2 which says that I2 is simply but I1 by 3. I2 is nothing but I1 by 3. Now you use this formula P loss is equal to I square R. Here P loss is at 11 kV. So first find the P loss at 11 kV. Then write P loss as 33 kV. So when we write P loss at 11 kV, we will use I1 square R. Do not confuse this I1 2. It is I1 square R. So let me erase all and I will see. So this is what? This is power loss at 11 kV. What is power loss at 11 kV? It is I1 square R. And power loss at 66 kV is I2 square R. I2 square R. Now simply as we have I2 is equal to I1 by 3, so simply replace this at I2 by I1 by 3. So I1 square by 9 into R. This I1 square R, this I1 square R is P loss at 11 kV. So this is P loss at 11 kV. So what we have? P loss at 33 kV is equal to P loss at 11 kV divided by 9. So we have what we have. We will ultimately what we get. Ultimately we will get that P loss 11 kV is equal to P loss 33 kV is equal to P loss 11 kV divided by 9. This we will get ultimately. Okay, so this is beautiful. Now let us come to our second claim. Suppose this is the voltage level at this is V1, this is V2. The a source or the load. So if we talk about the V drop, the voltage drop, which is V2 minus V1 divided by V2 minus V1, let the current flowing is R. So if we apply the Ohm's law, which is I is equal to V2 minus V1 by R, so which is V drop by R. So we have V drop is equal to I into R. This is clear. So voltage drop in the line is I into R. Now simply what you do is V drop 11 kV. So 11 kV is I1R, or V drop 33 kV. So 33 kV is I2R. Now from our previous slide we have I2 is equal to I1 by 3. I2 is equal to I1 by 3, and this I1R is V drop at 11 kV. So what we get? We get the relation. कि V drop at 33 kV is 1 by 3 V drop 11 kV. Is it not true? So this is beautiful. Okay. Now let us talk about cascade efficiency. See, cascade efficiency. See, in the generation, there is generation of power, then there is stepping up of power, then there is transmission of power, then there is distribution of power, then there is stepping down of power, then there is consumption of power. So there are several steps. Each and every step has its own efficiency, right? So cascade efficiency of the transmission and distribution line we are going to discuss. Okay, let eta 1, these are not n1, this is eta is represented for efficiency. Okay, so see, so this eta 1, eta 2, eta 3, eta 4, eta 5, eta 6, eta 7, eta 8, and so these are the efficiency of intermediate steps or intermediate stages in power generation, transmission, distribution and consumption. Okay, so please understand that the standard technical losses in India is 17%. So the efficiency of power in India is 83%, assumed to be 83%. In some states, due to theft or due to unmetered use of power or several other factors, these technical losses may go up to 50%, 17% to 50%, but in general it is considered 17%. Hence the power generation in India has an efficiency of generation, hence the transmission distribution efficiency in India is 83%, assumed to be 83%. This is T and D efficiency. Now see, you see, the thermal plants have the efficiency of 28 to 35%, which is say denoted by eta 1. Now the power is stepped up by using a step up transformer before transmitting, and usually the transformers has a efficiency of 99.5%, so assume it at 99.5%. now the EHV transmission has efficiency of 99%, and there are other transmission stages, say HV transmissions efficiency 97.5%. Sub transmission level, let us assume that the efficiency is 96%. Distribution, let us assume that the efficiency is 99.5%. Let the primary distribution assume the efficiency is 95%, and let the end user efficiency assume at eta 8. Okay, so cascade efficiency, see, here is the generating station. Okay, here is the generating station. Here is the generating station. Okay, here it is generating station. Now here it is transformer. Here it is transmission. Here again a transformer, and here it is load. Right? So the cascade efficiency here again, transformer 1, transformer 2. See that the cascade efficiency is talking about efficiency from this to efficiency from this to this. It is excluding the efficiency of generating station. It is also excluding the efficiency at consumer end. It is only considering the efficiency of the step up transformer, the step down transformer, the transmission and distribution network. So eta 2 to eta 7 it is only assuming. That is the cascade efficiency, which will come around 87%. Okay. If you multiply all these, you will be getting 0.87. If you multiply that with 100, you will be getting 87%. Okay. Now, let us, what is the efficiency at the plant level? Now we are interested in knowing efficiency up to the plant level. Means here the generating station, here it is T1, then it is T2, then there is load. So we are now interested in knowing the efficiency. Again, we are not going to consider this. This we are not going to consider. Okay. So we are actually considering this efficiency. क्या हो? What is the efficiency at plant level? We are also not going to consider this. Okay. So what is the efficiency at plant level? See, plant has its own network. Plant has its, any industry, any plant has its own network. It has their own transformer. Then the power is from the transformer, it goes to their panel room. Then from the panel room, it is distributed to several machines or several loads. Then the loads are mainly the pumps, the motors, the mechanical gears, etc. The mechanical system is considered to be having an efficiency of only 70%, and it is assumed that the losses in the mechanical system is 30%. Now it is assumed, let us assume that the efficiency of the internal transformer of the distribution transformer of the industry itself is 95%, and let us assume that the motors that are used in the plant having the efficiency of 90%. So if we talk about the efficiency of a plant or industry, we will simply multiply all these three efficiency. So that is 95% in the efficiency of the transformer of the plant, and then 90% is the efficiency of the motor, and 70% is the efficiency of the mechanical system. So if we multiply all these, we will get this at around 60%. Okay. Now let us talk about another important efficiency. This is generating station, this is the transformer, step up, this is step down, and this is the plant. Now we are interested in, we are again not going to talk about the efficiency here. Now we are interested in this efficiency of this part. Efficiency of this part. So this is, so basically from our previous discussion, we know the efficiency from here to here. This we know. How much? 17% is the technical loss in India, so it is 83%. And just now we have calculated the efficiency of this plant, which is around 60%. This is what we have calculated. So if we talk about the efficiency at the end of the load, in an industry, if we talk about the efficiency at the load end of the load, starting from the generating station, starting from the after the generating station till the consumption of power at the load, the efficiency will be 0.83 into 0.5985. This comes around 50%. Now this is very important. This will provide you an insight that will motivate you to save power. See, let us interpret this data. From generation to load, the efficiency has reduced to 50%. It means if 1 unit is generated, it is actually 0.5 unit at load. It means, so 1 unit generated at generating station becomes 0.5 unit at the load. There is one more interpretation. 50%. It means that 1 unit, if saved at the load, actually saves 2 units at the generation. This is amazing. So this ends our first lecture on our topic. In the next, we will be discussing few more concepts. Thank you.